So the wings of many insects move at a frequency which is dominated by the stiffness of the joint and the mass of the wings. This is a nice example of simple harmonic motion in the natural world. So let's do an example. Say the position of an insect's wing displaying simple harmonic motion can be roughly described by the equation below. The question is, calculate the frequency and period and then plot the position versus time graph of the wing. So what do we know? Let's write out the general equation for the position versus time relation for a simple harmonic oscillator. X of t equals a cos omega t. So what do we know? We know that a equals 0.005 meters or 5 millimeters. And we know that omega is going to be equal to 100 pi radians per second. Some useful equations here would be to remember that omega equals 2 pi f, and omega also is defined as 2 pi on t, where t is the period, which is equal to 1 on f, the frequency, and the frequency is conversely equal to 1 over the period. So to find the frequency and the period, we can use the expression omega equals 2 pi f, and from the equation we know that omega equals 100 pi, therefore 100 pi equals 2 pi f, and we can calculate that the frequency of the insect's wing is 50 Hertz. It's then simple to work out the period, as period is just the inverse of the frequency, so we can see that the period equals 1 on f, or 0.02 seconds. So what do we have? We've calculated the frequency and the period, so now we need to plot the position versus time graph of the wing, which we're asked to do in the question. It's always important to check back with the question to make sure you've done everything you need to do. So let's draw some axes, time, the period t, 2t, and our position, I've put this in millimeters, so we can put 5 and minus 5. Now we can draw on our plot. This is just our familiar cos curve. And let's add some numbers to the time axes. Our period that we've calculated above, t, is 0.02 seconds, and 2t will be 0.04 seconds. Now we have another question on simple harmonic motion. If a mouse on a spring is lifted up by 10 centimeters and let go, it will bob up and down, completing 4 oscillations in 10 seconds. The first part of the question asks us to calculate the frequency of the oscillations. So let's write down what we know. We know that there are 4 cycles in 10 seconds. The useful equations here would be that the period t equals 1 on f, and you might remember that the period t is the time for one complete oscillation. Now, we have 4 cycles in 10 seconds, so therefore we can calculate that t equals 10 on 4, or 2.5 seconds. Now, it's very straightforward to calculate the frequency. We just take the inverse of that number, and we see that the frequency equals 0.4 Hertz. The next part of the question asks us to find the position of the mouse at time equals 4 seconds. Let's write down some useful equations again. The position as a function of time, a cos omega t, omega equals 2 pi f. So what do we know? We know our frequency, we calculated that on the previous slide, and that equals 0.4 Hertz. And we know our amplitude, a, is 10 centimeters, and we'll put that in meters to put into the equation, so it's 0.1 meters. So x of t equals 0.1 cos omega, and we know that because omega equals 2 pi f, we can sub in 2 pi 0.4 t, and t is, in this question, 4 seconds. So if we put that in, we get this, which calculates out at minus 0.08 meters. So what we've found is the position is minus 8 centimeters at time equals 4 seconds. And the last part of this example asks, when does the mouse first reach maximum speed? Again, let's write down our useful equations. We've got the position versus time function, a cos omega t, and you may recall from the previous video that the velocity versus time is equal to minus a omega sine omega t. So let's write out our velocity equation again here, and we can see that v of t will equal a maximum when sine of omega t equals a maximum. And the maximum that sine of omega t can equal, of course, is 1. So if we put that in, we can find that v maximum equals a omega, or if we sub in our equation for omega, we can say that v maximum equals 2 pi fa, where omega equals 2 pi f. So now we have a relation for the maximum velocity, and we can put a box around that because that's quite a useful equation to know. But the question actually asks, when does the mouse first reach maximum speed? So to calculate this, we might need to draw a plot again. Let's draw our now familiar position versus time plot for a simple harmonic oscillator. We'll put the axes, the position axis in centimeters and the time axis in seconds. We'll add our period t. Here is our curve, and this is our function for x of t. We know at positions a and minus a, the velocity is going to be equal to 0. This is where the mouse is about to change direction. Points here, 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 and here on the curve. And as the mass passes through the equilibrium position in between these two extremes, the velocity will be a maximum. So v will equal v max. And this occurs here, 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 and here at x equals 0. So we can look to see where this first occurs, and that's here. So this is the first position where the object passes through equilibrium, or x equals 0. We know that our period is 2.5 seconds, so therefore this time here must equal 0.6 seconds. Therefore, the mouse first reaches maximum speed at t equals 0.6 seconds.